On this program, movement. First, walking. Then locomotion in robots. And in closing, computer-animated films. Movement is an ongoing obsession with humans. You only have to watch infants in their painstaking attempts to crawl, to walk, and at last to run about wherever they want. Walking is the result of a neuromuscular control we seldom think about. It is also the result of a long evolution. Walking upright as we Homo sapiens sapiens do is the culmination of a long evolution. Our human ancestors were mainly tree dwellers. When they had to get around on the ground, they leaned on their arms. When they had to hunt, however, to ensure their survival, they had to straighten their backs and raise their heads. Thus emerged the Australopithecines, early humans who walked on 2 feet. These bipedal hominids still walked slightly stooped over. Various improvements to their anatomy finally led to the emergence of Homo erectus. Homo erectus was the first human who was fully adapted to the upright posture. He walked more slowly than his quadruped ancestors. He had greater stamina, however, and could cover greater distances without tiring. His upright posture gave him a broader view of his surroundings. He was quicker to spot his prey and predators. Also, now that his hands were free, he could find new uses for them, such as tool making. Modern man learns to stand and walk in his first 15 months of life. He does this in a series of progressive steps. From the moment of birth, a baby's upper torso gradually gains strength. First, the infant is able to lift its head, then to raise its chest. And at about 4 months, the baby can sit with assistance. Once the baby is able to sit unsupported and to stand when leaning against something, he or she will make a greater effort to get around. A baby begins to get about by crawling on its tummy. And as the little legs get stronger, the baby will crawl around on all fours and gain speed. At about 11 months, most infants can walk, provided someone holds on to both hands. But it is only when they are able to keep their balance that they will begin to walk on their own. Gradually, their gait becomes less awkward. They walk with their feet closer together and take lower, longer, and faster steps. Usually by age 3, walking has become an automatism. The various movements involved in walking are produced by the action of the muscles. The muscles usually work in twos. Indeed, for every muscle actively involved in a given movement, there is a corresponding one that counters that movement. In walking, for example, the muscle involved in hip flexion, the right anterior, is called an agonist muscle. By contrast, the buttock, the muscle that produces the opposite movement, the extension of the hip, is called an antagonist muscle. Although it remains inactive when the hip is bent, the antagonist muscle offers some resistance to the movement. Whether agonist or antagonist, all muscles are composed of thousands of muscular fibers. Each fiber consists of a multitude of slender parallel threads, myofibrils. In turn, the myofibrils consist of 2 varieties of filaments: thick filaments composed of myosin protein and clear filaments of actin protein. For a muscle to contract, first the brain has to send electric impulses to the various muscular fibers belonging to that muscle. Once they have reached the muscular fibers, the impulses release a transmitter substance. The transmitter substance causes the actin filaments to slide over the myosin ones. That sliding motion causes the muscle to shorten, and in doing so, generates movement. The human muscle, a wonder of nature, gives us unparalleled dexterity and ease of movement. Some researchers would like to see their robots move just as gracefully. They are attempting to create artificial muscles to that end. The artificial muscles are composed of contractile polymer gel fibers. Gel fibers undergo abrupt changes in volume in response to small changes in external conditions. Some polymers, for example, will contract when immersed in warm water, and others when exposed to light. As for polyacrylonitrile fibers, they contract in an acidic solvent, but expand in an alkaline one. The researchers turned this phenomenon to their advantage and created a device consisting of multiple small perforated Teflon tubes. The tubes are evenly interspersed among the polymer gel fibers and convey an acid or base fluid to the various fibers. The contractions induced by this irrigation system are comparable to that of a human muscle. Besides the transplantation of artificial organ in humans, this new technology may one day be used to create humanoid robots. On Earth, the most useful form of locomotion is walking. Impressing this on robots, however, requires nothing short of computer and mechanical wizardry. One of a robot's main reasons for existence is that it can be used to reach and explore places inaccessible to humans. To walk on another planet, or even to journey through a human body. Those are the types of missions they are intended for. For space exploration, scientists designed a 6-legged robot. This insect-like robot adapts its mode of locomotion according to the terrain it encounters. It can get around in 3 different ways. Each mode of locomotion differs from the others in velocity, stability, and energy consumption. The fastest is the tripod gait, which is common to insects. It consists of lifting 3 legs at a time, as the other 3 push against the ground. When it has to go over rough terrain, posing some difficulty, the robot will choose another gait, using only 2 legs at a time. While slower, this new gait gives the robot greater stability. Should it run into a serious problem, such as a broken leg, for example, the robot resorts to its 3rd mode of locomotion. It then moves about very slowly because it only raises 1 leg at a time. To help it determine the gait it should adopt, the robot has a series of sensors in each leg. Some of these sensors measure the leg's velocity, and others its position. Ankle displacement sensors estimate the weight carried by each leg. The data gathered by these sensors is first analyzed by a small processor in each leg. The processor senses if the leg contacts the ground, hits an obstacle, or steps out into a void. The data is then transmitted to a central computer, which determines the robot's action behavior. The command is transmitted to the leg processors that induce locomotion when warranted. For instance, if the robot steps over a ledge, the computer tells it to back up. And should a leg hit an obstacle, it will be told to walk over it. And if the robot has to climb a steep hill, the processors in each leg produce just the right inclination for it to maintain its balance. With this kind of dexterity, mobile robots can explore many varied environments on their own. Robots can also be used to get into hard-to-reach places. For that reason, current robotics research has been focusing on the development of miniature robots. Big or small, all mobile robots consist of 4 main elements: a computerized system that activates behavior action, a series of sensors that perceive various environmental characteristics, motors to get around, and an energy source. Researchers concentrated on scaling down the size of each of these elements. They devised a behavior control system requiring very little in the way of computer equipment. This control system is based primarily on the data collected by a series of sensors, such as antennas that detect the presence of objects they come in contact with, or photoreceptors that detect light sources. With a small camera as another sensor, a small robot equipped with such a control system could be used to perform endoscopies. An endoscopy is a visual examination of an internal cavity, such as, for example, the large intestine. The micro-robot transmits what it sees on the screen through an optic fiber. Besides seeing the inside of the intestine on his screen, the physician can also guide the robot in its movements. Micro-robots are certain to become the medical instruments of the future. But for that to happen, we will have to be able to make them even smaller. In their efforts to do so, scientists have developed a tiny piezoelectric motor, only 2 millimeters in diameter. The motor is composed of a ring made of a ferroelectric material. Ferroelectric materials have a particular property. They buckle when a potential difference is applied at their extremities. When the motor ring is subjected to such conditions, a wave of deformation travels through it. When a lens is placed down on the surface of the vibrating ring, the force of friction between the ring and the lens causes the lens to rotate. Considering all of these technological advances, perhaps the day is not far off when an entire robot will fit on a single silicon chip. It was only with the advent of the computer that robotics really began to move ahead. Computers not only animate robots, they also give life to drawings. Computers provide artists with the means to recreate the figments of their imagination in moving images. They allow them to draw them, color them, and even give them life by animating them with movement. What makes all this possible is a powerful computer program. The painter has his canvas, palette, and paintbrush. And the creator of animated films has his computer screen, a software program, and a mouse. As he creates an object, he can see it under various angles on his computer screen. Moreover, the animator can bring it closer or move it farther away. He can even make it rotate so he can view it from every possible angle. First, the animator creates an object. He then proceeds to animate it. Animation basically consists of making certain features of the object, such as its shape, color, texture, and position, vary over time. One technique used to produce such effects is keyframe animation. Using this technique, the animator need only create a few drawings of the object. These drawings constitute the keyframes. The computer will automatically create all the intermediate images between the keyframes. This technique can also be used to move an object in space at the same time as it is undergoing multiple physical transformations. To achieve this, the animator begins by outlining the object's future path in space. Then, at various points along that path, he draws the new shapes the object will take on. The computer then produces all the images in between. The program also allows animation of several models of the same object simultaneously. This greatly facilitates the creation of such complex effects as fireworks and sprinklers, for instance. First, the animator has to determine the characteristics of a particle at its starting position, as well as those at its terminating position. He must also specify how many models of that particle he wants, their trajectory, relative position, along with other parameters such as the duration of the itinerary. Using all this data, the computer is able to create a very coherent animation in very little time. The movements of an animated figure are very complex due to the many joints in the human body. Thanks to the animation computer program, movements are easily simulated and with stunning realism. The animator begins by creating a skeleton in the form of a chain. Each link in the chain represents a section of the body. The animator then animates the skeleton simply by moving either of the chain's ends in the direction he wants. Through inverse kinematics, a technique based on the principles of robotics, the intermediate joint rotations are automatically computed. To give his character's body, the animator can attach flexible envelopes to the articulated chain, such as muscles and skin. Again, by inverse kinematics, the movements of the joints automatically bend and inflate the various envelopes. These movements match the joint movements perfectly. Bending occurs near the joints and inflation, more or less pronounced, between them. But one of this program's key advantages is that it allows animation of a fictitious character directly from the movements of a real person. This option, however, requires a device that is able to record the gestures made by the real person. A dancer, for example. The device consists of a transmitter, which generates a magnetic field, and a series of sensors that the dancer wears on his head, back, hands, waist, and feet. The sensors act like small compasses. They determine the position of the body parts in space based upon the strength of the magnetic field they are experiencing. Signals from each of the sensors are sent to the computer, which interprets them and identifies the various positions and orientations of the dancer's limbs. It then displays them at the corresponding parts on the articulated skeleton. The animated figure then performs, in virtually perfect synchronization, the same movements as the dancer. A similar mechanism allows animators to animate the facial expressions of a synthesized figure. All they need is a microphone. The microphone transmits the animator's voice into the computer, which translates the vocal signals into lip movements and facial expressions, which it reproduces on the animated figure. This computer program's greatest feature is its user-friendliness. It is a major advantage because it allows animators to devote more time to the act of artistic creation. Computers are at the heart of robots, of fantasy. They are at the heart of our factories and of the arts, technology, and science. It's the computer age. During the last 20 years of the 20th century, 80% of all manual work will have been taken over by computer technology. Will the millions of newly unemployed be able to maintain a sense of dignity?